Good morning. So this is our 8th lecture. In the previous lecture, we have been discussing about the aircraft air conditioning cycles. We have discussed about simple aircraft air conditioning cycle, bootstrap aircraft air conditioning cycle. We found that simple aircraft air conditioning cycle does not work at higher Mach numbers. Of course, it works at higher Mach numbers, but at higher Mach numbers, whatever the temperature of the air we get at the exit of turbine, that is significantly higher, so of course it will not be leading to effective cooling. Okay, so the cycle which could actually avoid this limitation of the simple aircraft air conditioning cycle, that was nothing but bootstrap cycle. Okay, so now there is one more cycle which is called as regenerative aircraft air conditioning cycle, and again regenerative aircraft air conditioning cycle is having performance similar to that of bootstrap cycle. So it means this is nothing but the slightly simpler variant of the simple aircraft refrigeration cycle with one additional heat exchanger where we do cooling by regeneration, but its performance is similar to that of the bootstrap cycle. So it means we need not to use the additional compressor and cooler stages. Okay, so let me draw the schematic representation of this cycle. So in this cycle, of course, in aircraft cycle, this is how we have the body of the aircraft engine, and then we have nothing but, okay, so we have one compressor over here, then we have turbine, and we have one combustion chamber. Okay, now in terms of working fluid, we see that air comes from 1 to 0.2 because of ram effect, its pressure and temperature increases. Then when it enters to compressor, from the compressor it comes out at 3. Some amount of air goes to turbine after the combustion chamber, and remaining amount of air, what we do, we over here cool, and this cooling we do with the help of what? Ram air. Okay, so with the help of ram air we do some cooling and it comes to 0.4. Now in case of regeneration cycle, if you recall your earlier case, whenever I am just simply talking about the reverse Brayton cycle or Joule refrigeration cycle. Okay, so in Joule refrigeration cycle also I have explained you one variant which was nothing but regeneration cycle. Okay, so what we were doing in regeneration cycle, after this cooling heat exchanger we were putting one additional heat exchanger, and in that additional heat exchanger basically whatever the air was at the exit of the evaporator, okay, that air was being used to cool this particular air. Are you remembering that one? So if you just refer to Joule cycle with regeneration. Okay, so not exactly the same, but in a similar way, what we will do, we will now put one additional heat exchanger over here. So I have put one additional heat exchanger, and of course over here my aim is to cool the working fluid. So in this additional heat exchanger I will further cool the air from 4 to 5. Now this cooling has to be done with the help of some another working fluid. There in heat exchanger there has to be some other fluid which will be taking the heat from this. What is that fluid, how that will be coming, that I will discuss slightly later. But now after this, what we can do, after the cooling process we can do expansion. So now I will be doing expansion in the turbine. Okay, so 5 will lead to 6. Now what I will do, whatever the air I am having at 0.6, I will bifurcate it into two parts. Okay, one part I will be sending to cabin for cooling, where 6 will become 7, and a fraction of this air will be passed through this heat exchanger and it will be used for cooling from 4 to 5. Is this point clear? All are agreeing to this point? So now you can see that we have one limitation. This point 3, it can be cooled maximum up to which temperature? Please tell me, when I will be cooling from 3 to 4 in this first heat exchanger with the help of ram air, to what maximum temperature I can cool? T2. maximum I can cool up to T2, and T2 will be, because of the RAM effect, T2 will be greater than the atmospheric local outside atmospheric temperature. Okay, so it means that I have limitation over here. So to avoid this limitation, what I have done, I have taken the air from the exit of turbine. So exit of turbine, it means I have done the expansion process. So after the expansion process, my temperature will be low. So temperature of 6 will be significantly lesser in comparison to temperature of 2. So that's why that I have partly used, and this is the additional heat exchanger, which is typically called as regenerator. Regeneration means from own energy itself you are trying to create some additional cooling. Okay, so that's why we are calling it as regeneration. So that is the reason additionally we were able to cool from 4 to 5. Okay, so now let me draw it on the cycle. So on TS plot, this is ideal 1 to 2 process. Actual will be slightly deviated 2 dash. Then this is ideal 2 dash to 3 process. Actual will be deviated at point 3 dash. Now what we were doing? We were cooling actually. Okay. So the initially cooling was done from 3 to 4. If I have only the simple cycle, then I will be just doing expansion from this. Okay, but if I have regeneration cycle, then in this regeneration I will be having actually further cooling from 4 to 5, and from 0.5 I will be doing expansion to 0.6 in an ideal process, and 0.6 dash in an actual process. Okay, and then from here 6 dash to 7 I will be having actually this one Kevin cooling. Is this one here? All are clear with this cycle? So this type of cycle is nothing but called as regenerative aircraft air conditioning cycle. Okay. The only benefit over here is that whatever the cooling air we are using, that is only employed for further cooling of the working fluid from 4 to 5 in the regenerator type heat exchanger. Is this one clear? But there is small penalty. Now, if say whatever the fraction is required for cabin cooling in the turbine, I have to take working fluid slightly more than that. Okay, then only I will do it effectively. And of course, this turbine will be producing some amount of work. So maybe for that I will be using a fan, and that fan will be used then for allowing this flow of air. Is this one clear? Now one more cycle is left. What is that cycle? Please tell me. Subatmospheric aircraft air conditioning. What we do in atmospheric cycle, again a simple variant. Here we use basically two turbines, multi-stage expansion. Okay, how we do that, let me explain. This should be now very clear to you because we have multiple times drawn this one. Okay. What I am having over here? I am having RAM here, which is coming at pressure P2 and temperature T2. Okay. And of course, the RAM air pressure and temperature is slightly larger in comparison to pressure and temperature of ambient condition. Okay, one. Now what I'll do, because this point T2, whenever we initially cool the working fluid after the compression, this we cool with the help of ram air. Okay, so basically the temperature of ram air T2 is a limiting condition which limits the actual cooling of gas in the heat exchanger. Okay, so what I will do, instead of directly passing the ram air over the heat exchanger, I will first pass it over a turbine. Okay, so I am passing ram air over a turbine. So if I pass ram air over a turbine, what will happen? There will be decrease in its pressure and temperature. Okay, and after that, whatever the air was coming from 3, okay, this high pressure air was coming at temperature T3. Now I have passed it through a heat exchanger. Okay, now I have passed it through a heat exchanger. And what I can do now, this ram air which is now further cooled, I can pass it through this heat exchanger for cooling process. So now I will be having cooling over here from 3 to 4, but earlier the limiting condition for T4 was that it can maximum go up to T2. But now this T2 I have further cooled down to some temperature 2 dash. Okay, 2 dash I have cooled it down. So it means T4 can now go up to T2 dash. Whereas T2 dash is significantly smaller in comparison to T2 because I am doing the expansion process. So in the expansion, there will be significant fall in temperature of the ram. Okay. Now this is the reason whenever we do the expansion in the turbine, this expansion process actually leads to significant decrease in pressure as well. So pressure of P2 is large, P2 dash is very small. Okay, so because of this, P2 pressure goes even below the local ambient pressure. So that's why cycle is called as sub-atmospheric cycle. Is this one clear? Now, from point 4, what I need to do? Please tell me. Turbine. So 4 to 5 is turbine, and then 5 to 6 is cabin. All are clear with this? And of course, this turbine and this turbine will be doing some amount of work. That work we will be utilized to rotate a common fan. So what I can do, I can use some gear arrangement. I can use some gear arrangement which can couple the output of these two and run a. Okay, all are clear with this? Of course, I have made it complicated gear arrangement. It should not be that much. We can place our turbines in such a way so that either both are lying on same shaft, then we need not to use additional gear arrangement, or say if these are perpendicular, then with the help of a simple bevel gear, I can actually, single bevel gear set, I can connect these two. So that's a basically design aspect that we are not looking at present. Is this point clear? All are clear with this point? Now can you draw the sub-atmospheric cycle? What will happen? While drawing the sub-atmospheric cycle, we need to take care of one point. This is 1 to 2. Two dash, then 2 dash 2, 3 is ideal, and 2 dash 2, 3 dash is actual. Okay. Now, whenever the cooling will take place from 3 dash, this cooling will take place in such a way so that the temperature of point 4 is lesser than temperature of point 2. Clear? All are clear with this point? In simple aircraft air conditioning cycle, I have to stop cooling somewhere above T2. Okay. In ideal case, if heat exchanger is 100% efficient, then it can maximum come up to 0.2. But here it can go below this because already the RAM air I have cooled to temperature below the T2 temperature. All are clear with this point? Anyone is having any doubt? Now you can see that earlier if you were reaching to T2, from there you were doing expansion. Now you are doing expansion from point 4. Okay. So what is the meaning? Meaning is you are doing expansion across the same pressure ratio, but your inlet temperature which you are considering at the inlet of the turbine, that is less for this case in comparison to standard cycle. Okay, so in bootstrap cycle what we did? In bootstrap cycle we started expansion temperature almost at the same condition, but the pressure ratio across which we have done expansion, that was actually large. Are you getting this point or not? So in the bootstrap cycle, if you recall, my starting temperature was almost same as that of the simple air conditioning cycle. Okay, but the only difference was the pressure ratio across which I was doing expansion in the turbine, that was large. So because of large pressure ratio, temperature at exit of turbine was decreasing. Okay. However, in this case, which is sub-atmospheric cycle, the pressure ratio across the turbine is same as that of the pressure ratio in case of a simple aircraft air conditioning cycle. The only difference is the inlet temperature of working fluid to the turbine is significantly small in comparison to the inlet temperature in case of what? Bootstraps. Simple cycle. Okay, so that is how we are able to do the more effective cooling. So now we have actually whatever points I am saying, all of you have seen now all the 4 cycles, so you can yourself now try to make such comparisons why performance is actually better for one particular type of cycle. Okay, now whenever we do compare these cycles, ultimately what we will be doing, if we have 4 type of cycles, of course for their performance we have to compare these 4 different type of cycles. So for comparing these 4 different cycles, we have one parameter which is called as DART. DART is called as dry air rated temperature. Okay, so what is the meaning of DART? DART. Whenever in all the 4 cycles, can you tell me which temperature is standard which will be controlling the cooling process? We have multiple temperature, some temperature at inlet to turbine, some temperature at exit of cabin, some temperature is outlet of turbine, inlet of cabin. So among all the temperatures, which temperature you feel is actually our desired outcome and that has to be achieved in any case? Where? Yes, exit of turbine and inlet of cabin. That is the temperature which will be actually governing that how our temperature is there inside the cabin. So it means we have to control temperature at the exit of the turbine. Okay. So the temperature of the air at the exit of turbine is something which is called as dry air rated temperature. And dry air rated temperature is a parameter which typically is used for comparing the performance of different aircraft air conditioning cycles. Whenever we have to make the relative comparison. Okay, so for relative comparison, some basis should be there. So that basis is actually dry air rated temperature. And what we defined this is nothing but the temperature at the exit of turbine. Okay, so now if you compare, let me plot DART along this side in degree Celsius Let me consider, say this is 0 degree Celsius, this is minus 20 degree Celsius, say minus 40, 20 degree Celsius, 40 degree Celsius, 60 degree Celsius likewise. Okay. And along this side I am having nothing but Mach number. Mach number M1. Particularly I am talking about Mach number M1. Okay. So here my Mach number should start somewhere close to 0.4, because generally all the aircrafts are operated at the high speed. Even if we have subsonic aircraft, I cannot go below 0.3 Mach number. So it somewhere starts from 0.4, then say somewhere over here it is 1.2, then likewise it is increasing to 3, 4 or 5. Okay. So for the case of a simple aircraft air conditioning cycle, initially at low Mach numbers, the temperature start is say close to minus 20 degrees Celsius. However, at Mach number of 1.2, it becomes somewhere close to 10 degrees Celsius, and then it significantly keep on increasing. So this is nothing but simple air conditioning cycle, simple aircraft air conditioning. Is this one clear? So now earlier what I told you, that if I am somewhere close to 1.7 Mach number, then close to 1.7 Mach number my temperature is close to 25 degrees Celsius. Okay. So if I go above than that, then simple cycle will be giving me temperature at exit of turbine dart value greater than 25. Will it be doing effective cooling? Not doing. So that's why it is used for low Mach numbers. Now let me talk about the bootstrap cycle. Okay. So in case of bootstrap cycle, you will be finding starting temperature is even further low, and it goes something like this. So this is bootstrap cycle. Then we have next one, regenerative cycle. Regenerative cycle, it will be starting somewhere here. This is regenerative cycle. Then what we have next? Subatmospheric cycle. Subatmospheric cycle, it goes something like this. This is called as, this is the actually dart variation with Mach number for subatmospheric cycle. Then what we have next? Only these four? There is one more additional variant. Let me explain to you. This is called as regeneration with evaporative cooling. So the most effective cycle among all is regeneration with evaporative cooling. Okay. So this cycle is nothing but a simple regeneration cycle. However, in case of simple regeneration cycle, what we did? We use, in simple regeneration cycle, we use the additional heat exchanger, and in this heat exchanger we have taken some fraction of air from the exit of turbine. So instead of taking this fraction from exit of turbine, what I will do, I will not use this air, but here I will use some another type of low temperature organic fluid which has boiling point very less. So that fluid I will be passing through heat exchanger. So what will happen? If a low boiling point fluid will be passing through this, that will be gaining the heat from the air. And because I am passing a liquid fluid over here, so because of the liquid passing of the liquid fluid, heat transfer process will be more effective. That's why dart for the cooling in this process will be very effective, and dart will be very less at all the metals. Is this one clear? So regeneration cycle with evaporative cooling, the only difference is that in this second regenerative type heat exchanger, whatever the cooling medium I am considering, that cooling medium is some externally low pressure or externally low boiling temperature cooling liquid. Okay, so if its boiling temperature is low, whenever it will be exchanging the heat, it will try to evaporate. And because it is in liquid phase, its conductivity will be significant, so that's why the performance of the heat transfer process will be effective. So in such scenarios, it will be leading to significant decrease in the dart. Of course, don't go with the numbers because I am not drawn the graph with exact scale, so that's why there can be some issues with the numbers, because generally for air conditioning we will not go up to very low temperatures close to -40, we will be staying close to -20 degrees Celsius. Okay, so that's why this diagram is slightly shifted in the downward direction. So numbers you can refer from the actual diagram in the textbooks. Is this one clear? All are clear with this? So this is how you can compare the performance of different aircraft air conditioning cycles. Okay. Now, of course, with this our second unit on air refrigeration cycles or gas refrigeration cycles or air conditioning cycles is actually over. Okay. As per our syllabus, of course, if you go to your textbook, you will be finding one more topic on gas refrigeration cycles, which is about the liquefaction of the gases. Okay, so it means if you have to liquefy different constituent of gases, then also these cycles are preferred. But of course, that is not in our syllabus. Mostly that is important for cryogenics applications. Okay, so we are not looking into the cryogenics below temperatures -60. So that's why we will not study that topic over here, and that is not in our syllabus as well. Those who are interested, you can refer to your textbook. Of course, now we will start with the next unit, which is vapor compression refrigeration cycle. But before that, let us discuss the numerical problem which I have given you in the previous class. So all of you have solved it? You were able to solve it? How many of you have solved? Please raise your hand. Okay. So did you get the solution from book or you have tried by your own? Temperature pressure you have calculated. Okay. What about you? Okay. Okay. So from book or by your own? Okay. Now let me then, majority of you have not done, so let me actually start with the question. So can you read the statement so that I can write some numbers? Okay, before that, the problem was on simple aircraft air conditioning cycle. Okay, so let me first draw the simple aircraft air conditioning cycle so that I can note down the various parameters whatever are given. Is this one clear? So cycle is correct. Okay. The question was, an aircraft is flying at a speed of, so it means velocity of aircraft, it means V1 is equal to 1000 kilometers per hour. Okay. So if you try to convert it into meters per second, how much it is? 1000 divided by 3600. How much it is? And also into 10 to power 3. Okay. So how much is 277.8 meters per second. Okay. Then the ambient temperature and pressure are. So what is ambient condition? T1. So T1 is how much? Minus 15 degrees Celsius. In Kelvin, if you calculate, it will be 273 minus 15. How much? Why I am converting it into Kelvin? Because later on I have to apply T2 by T1 relation in terms of gamma by gamma minus 1. So of course that has to be in Kelvin. Okay. And what is the pressure at inlet? 0.35 bar. Then next statement is compressor, turbine and ram efficiencies are. So compressor efficiency is 0.8, turbine efficiency is 0.8 and ram efficiency is 0.85. Okay, so these three different efficiencies are given. What next? The pressure ratio of the compressor is 5. Okay, so it means across compressor, it means P3 by P2, P2 dash is 5. Is this one clear? Compressor ratio, pressure ratio across compressor is 5. Then what else? The effectiveness of heat exchanger is 0.8. What is the symbol for effectiveness? You have studied heat transfer. Epsilon. Okay. So epsilon of the heat exchanger is equal to 0.8. Is this one clear? Then what else? Pressure drop in the heat exchanger. Now delta P. So for heat exchanger, let me write Hx. Delta P heat exchanger is 0.1 bar. All are clear with this? Then the cabin pressure is 1.06 bar. What it means? P6 equal to 1.06 bar and cabin temperature is 25 degrees Celsius, which is T6, 298 Kelvin. Okay. Then what else? Assuming simple aircraft air conditioning cycle, first part is we need to determine pressures and temperatures at various points. That is the first one. Okay, how to start with? I know pressure and temperature at point 1. How to calculate pressure and temperature at point 2? Velocity. So I know that T2 is equal to T1 times 1 plus Mach number. Okay, Mach number times, or let me write V1 square by 2C. Is this one clear? That is the relation. So T1 will be outside or T1 will be, there will not be any bracket actually. Okay, this one is clear. Now what is T1? 258. V1 square 277.8. 2 times, what is Cp? So we are considering air as working fluid. So assume Cp of air 1.005. Okay. 1.005 is in kilojoule. And this unit is in SI unit. So I need to multiply with 10 to power 3. How much is the value of T2? 296. Okay. So 296.39 is as per the solution. Okay. What else? Can I calculate pressure now? How? 1 to 2 ram is nothing but a compression process, isentropic compression process. So P2 will be P1 times T2 by T1 power gamma by gamma minus 1. Okay, what will be gamma? Gamma will be 1.4. You know T2 now, you know T1, P1 you know, and gamma is 1.4 for the gas. What is the value of P2? How much? 0.57 bar. This is the value of the P2. But actual other point, the actual point is what? P2 dash. Okay, because process is not isentropic, and this is valid only for isentropic process. So now what I am having additional information? RAM efficiency. RAM efficiency is what? P2 dash minus P1 divided by P2 minus P1, and its value is how much? 0.85. From here I know this value, this value, this value, so I can calculate P2 dash. How much is it? 0.53. Correct. 0.536 bar is given in the solution. Okay. Now what else? After this, what I am having? I know now the P2 dash, which is the pressure at the inlet of compressor. Okay. Exit of compressor is 0.3 and pressure ratio is given 5. So P3 will be equal to 5 times of P2 dash, which is how much? P2 dash, because inlet is P2 dash. Okay. So from this I will be getting P3 as how much? Please tell me. P2 dash into 5. Please calculate. 2.68 bar. Okay. Now what I need to do? I need to calculate T3. How I can calculate T3? Process 2 dash to 3 is isentropic. 2 dash to 3 process is isentropic. Okay. So for isentropic process I can say that T3 will be equal to T2 times P3 by P2. Yes, sorry. P3 by P2 dash power. What I will be getting? Gamma minus 1 by gamma. How much is it? 469 point. As per solution, 469.42 Kelvin. All are clear with this point? Anyone is having any doubt up to this point? Okay, but this is temperature of 0.3 if I go in isentropic fashion. But I have been given some value of isentropic efficiency of the compressor. So what I need to do now? I need to utilize that to calculate temperature of 0.3 dash. कहाँ पे? Okay, T2 dash I have calculated. Okay. You can calculate T2 dash also very easily now. Okay, so what will be efficiency of compressor? T3 dash T3 minus T2 dash divided by T3 dash minus T2 dash. In compressor, actual work is more, ideal work is less. Okay, so 2 dash to 3 is the ideal work and 2 dash to 3 dash is the actual. Clear? So what is compressor efficiency? Tell me. How much is it given? 0.8. T3 we have calculated 469.42. T2 dash, have I calculated T2 dash or not? Okay, so now I need to also calculate T2 dash. How you can calculate T2 dash? Please tell me how you can calculate T2 dash. From RAM efficiency. RAM efficiency is always given in terms of pressures. Okay, RAM efficiency is not given in terms of temperatures, because RAM effect is majorly the conversion of kinetic energy into pressure energy. Is this point clear? However, one important assumption you can make over here. Calculate the pressure ratio of P2 dash by P1. How much is pressure ratio? What is the pressure ratio of P2 dash by P1? P2 dash you have calculated, and P1 I have just given in the question. 1.53. Okay. So the pressure ratio across the RAM effect is very, very small. If pressure ratio across the RAM effect is small, the point 2 and 2 dash will be, because what happens? This has to be at slightly higher pressure and it has to be at slightly lower pressure. Are you getting my point or not? Okay, because in ideal RAM compression process, the increase in pressure will be more. In actual process, there will be some penalty because of irreversibility, and decrease in pressure will be less. So what will happen? This point 2 dash will lie on a smaller pressure line, slightly lesser pressure line. And in this way, if pressure ratio is small, these two lines will be so close to each other that temperature of T2, despite a slight decrease in pressure, can be approximated nearly equal to T2. All are agreeing to this point or not? What I have explained. Is this one clear? Okay. So it means that what I can do, I can write that. Where is T2? Yeah, T2 is nothing but nearly equal to T2 dash. Point is clear? So what number I will be getting over here? 296.39 divided by T3 dash minus 296.39. From here, what will be value of T3 dash? Please tell me. How much? Please do calculate fast. 512.68 Kelvin. Those who are not understanding the question, ask at this moment only. Okay, because this is important question. It is giving us idea about the complete cycle. And at present, what I am doing, nothing. It's a simple thermodynamics. Okay. At present, I have not gone into refrigeration. Okay. So basically, this is the isentropic RAM process. So in isentropic process, this will be somewhere here. I will be having one constant pressure line. Okay. In actual RAM process, what will happen? Pressure will be slightly less in comparison to the ideal process because of inefficiency. Okay. So wherever I am having 2 dash point, the pressure line which is passing through point 2 dash will be this one. Is this point clear? Now, if you see, point 2 was on high pressure line, point 2 dash is on low pressure line, and these two lines are adjusted in such a way that this low pressure line is shifted towards right with reference to point 2. Okay, so in this way, point 2 and point 2 dash will align almost on the same temperature conditions for small pressure ratios. Okay, if pressure ratio is significant, their effect could be significant. Okay, but for small pressure ratios, this will be minimized. This effect will be minimal, and it will be almost, temperature will be almost same. Okay, up to T3 is it clear? What else we need to do now? 4. I need to calculate 4. How to calculate T4? To calculate T4, we need to understand the process of heat exchanger. So this is the heat exchanger. In the heat exchanger, one fluid is coming at temperature T3 and it is cooled to temperature T4. But what is used for cooling it? For cooling it is used the ram air which is coming at temperature T2. Of course, whenever the ram air is taking heat, then other end of ram air will be at slightly higher temperature than T2. Okay, so what is the lowest temperature of the cold stream available in the heat exchanger? T2. So it means that the maximum temperature of hot stream, which is T3, if heat exchanger is 100% effective, then it can maximum go up to temperature of T2. Okay, so maximum amount of decrease in temperature within the heat exchanger of working fluid can be from T3 minus T2. However, what is actual heat transfer? Actually, if we see, the hot fluid is changing from T3 to T4. So actual heat transfer is T3 minus T4. So actual divided by maximum is something which is effectiveness of the. Is this point clear or not? Shall I explain it again? I have a heat exchanger in which hot fluid starting at temperature T3 and is being cooled to temperature T4, and this is being cooled with the help of ram air which is coming at temperature T2 and leaving at some temperature T2 dash. Okay, so now the heat exchanger will be 100% effective when the highest temperature of hot stream is cooled down to the lowest temperature of the coldest stream, coldest temperature. Okay, so it means the ideal condition is T3 temperature should reach to T2. So that is ideal heat transfer, but in actual practice it is being cooled only up to temperature T4, which is larger than T2. So T3 minus T4 is this. So this is how much? I know T2, I know T2, I know T3, I know this one. So from here what I will be getting? T4, how much? And please remember, this will be 3 days. This should be 3 days because our heat exchanger inlet is actually 3 days in an actual process. Okay. So T4 is how much? Please tell me. How much is T4? $339.65 Kelvin. Okay. Then what else? Pressure. What will be pressure at point 4? P3 dash is the pressure at the inlet of heat exchanger minus pressure drop delta P. Okay, because at the inlet of heat exchanger pressure will be more, then whatever is the pressure drop, that will be subtracted to calculate pressure at the outlet. So it will be nothing but 2.68 minus 0.1 and it comes out to be close to 2.58. Okay, so 2.58 bar is the pressure at point 4. What else is there now? T5. How I can calculate? T4 times P5 by P4 power. It is how much? 263.43 Kelvin. Is this one clear? Now what else? Efficiency of turbine. What is efficiency of turbine? Please tell me. T4 minus T5 dash divided by T4 minus T5. From here I will be getting T5 dash, which is how much? 274.86 Kelvin. Okay. And after that, what is the next question? So I have calculated pressures and temperatures at all the points. What is the next question? Next question is mass flow rate of the air. Okay, yeah, COP is also there. Okay, so what will be COP? What will be COP? Please tell me. What will be COP of this cycle? Please tell me. Refrigeration effect. What is refrigeration effect? How much is refrigeration effect?
Cp T1 minus T5.
On per kg basis, it is Cp, not T1 minus T5. It is T6 minus T5 dash. Please see the cycle. Air is coming at T5 dash and maximum it is, cabin temperature is 25. Okay, so refrigeration effect will be on per kg basis, it will be Cp into divided by W net on per kg basis. What will be W net? Compressor work minus turbine work. Will there be any role of the ram work? Will there be any role of ram work on calculation of W net for defining the COP? Those who says it should be there, please raise your hand. Those who says it should not be there. So 3 people are saying it should not be there. 1 is saying it should be there. What about remaining? Please tell me, what about remaining? It should be there or not, or you are not able to understand what I am explaining? नहीं होना चाहिए, or you are not understanding? Yes, RAM work should not be included. Why RAM work should not be included? Because RAM work is happening because of a spontaneous process. We are not having any additional shaft where we are giving some input power to do the RAM work. Okay. It's actually work done on the system. Yes, it is happening on the system, but it is happening because of what? It is happening because of the propulsion of the aircraft in the forward direction. So it means its penalty is coming on engine power. Okay, its penalty should come on engine power. It's not a desired outcome for our refrigeration system. So in refrigeration we are not using it anyway. Okay, so of course RAM work is nothing but a penalty. Okay, but that penalty is coming on what? That penalty is coming on main engine of the aircraft to propel it in the forward direction. While propelling it in the forward direction, there I should consider this penalty. Okay, so maybe you all know about all the terminal temperatures. Other parts please try to solve, and otherwise I will discuss in the next class.